Okay, this is our fourth and last lecture on rotational mechanics, which is looking at angular momentum. Now, with every quantity in rotational mechanics, there's always an equivalent linear one, and this is obviously momentum. So I want you to think about what happens with a particle that's travelling in a nice straight line of mass m and velocity v, and also what's happening with an object that is rotating. It's rotating with omega, and it has a moment of inertia of I. Well, a little bit like a particle, this particle will always continue to go at the same velocity and continue that velocity unless a force acts upon it. That's Newton's first law, in effect. So, and I suppose similarly, our analogy is that this object will keep rotating at angular velocity omega unless a torque is exerted upon it. So if we think of ourselves as linear quantities on this side and rotational on this side, let's draw some parallels towards of them. Well, I suppose the first one we want is Newton's first law, which suggests that the velocity is constant, I hope you're okay with these abbreviations, if the resultant force acting on the system is zero. And I suppose that's the same we can say here, that this continues to rotate at an angular speed omega, which is constant, unless there is a resultant torque acting on it. So if there's no resultant torque, then we have a constant rotational speed. If there is no rotation, if there's no resulting force, it carries at a constant velocity. Good, okay, and if you remember Newton's big idea, his big idea was momentum. He didn't start with concepts of force, he started the concepts of momentum. So momentum in this case is mass times velocity. And the equivalent rotational momentum, or angular momentum, is given the symbol L, and is equal to the moment of inertia multiplied by the angular speed. We ought to really just give this a sense of what it is. This is the angular momentum, and it's given the units of kilograms meters squared, that's what the moment of inertia is, radians per second. That's quite a mouthful for a unit. Good, okay, now Newton's big idea, of course, was the rate of, if that were Newton 1, Newton 2 is that the force gives rise to a change in momentum with respect to time. And therefore, the equivalent, I hope you have understood that and we've come across that before, or in other words, F equals ma, if you like, which is a simpler way of writing it. And therefore, similarly, if a torque is exerted on this rotating object, then that will give rise to a change in its angular momentum with respect to time. Or you could say the rate of change of angular momentum with time is how much torque is being exerted. This, of course, gives rise to I d omega by dt, which is the same as I alpha, and that's where our expression torque I alpha comes from. Similarly here, F equals ma. Okay, and then finally, the last thing that we really need to talk about is what happens with collisions. We often say that the momentum before the collision must be equal to the momentum after the collision, and that's the same for rotational mechanics as well. The angular momentum before a collision must equal the angular momentum after a collision. And of course, this is where life gets interesting. Because unlike ordinary momentum, where you can't change the mass of an object without getting involved in the system, you can change the moment of inertia of the system because the moment of inertia is proportional to the mass and the radius where that mass is held. So therefore, by redistributing where the mass is, you can change the moment of inertia and therefore change the angular momentum. And so you can get certain effects. Let's talk about a couple of them. Okay, first and foremost is, say, ice skaters. When they spin around. And I can't draw an ice skater, but I can show you an experiment which might be used in the classroom. Let's imagine you have a turning stool. You can try this on your own if you want. Somebody's seated on this turning stool, my stick man, and they're holding two weights. Let's imagine that on same and he's given a rotation of sorts. Let's imagine on the same stool now. Oops, let's run that in. It's meant to be the same person, you know, suddenly looking larger. They then draw the weights towards themselves. Then what's going to happen? Well, if you can imagine this sort of momentum idea from angular momentum before must equal the angular momentum afterwards, that means that moment of inertia multiplied by the angular speed must equal to, and I'm going to write this more, moment of inertia times the angular speed. In other words, this has become larger. He's moving fast. He has a faster angular speed. Why? Well, moment of inertia is proportional to mass times the radius squared. So if he's reduced the position of the mass, then the moment of inertia has got less. To compensate for this, of course, he has to be moving faster. And that's why ice skaters, when they draw their arms in or their legs in, they start to spin faster. Good. Okay, what about another example? Well, if you had systems with rotating disks, on a spindle, this is rotating at a speed omega, and then suddenly we drop on it another disk which has its own moment of inertia, then you can imagine this is acting like a collision. So we must say to ourselves that moment of inertia, angular momentum before must equal angular momentum afterwards. We initially have a moment of inertia and angular speed, but that must be now a new moment of inertia multiplied by the angular speed. Nu. Quite often this is going to be reduced, so omega is greater than omega nu, because this invariably is going to be larger than that. If you can take it off, then of course you'll increase. This is how clutches work, clutch systems. You have the car engine revving and spinning around, and then you introduce another disc which is connected to the wheels and the gearbox, and moving it back and forth is the clutch pedal. Okay, so these are two very obvious examples of where we have this conservation of angular momentum, how it starts to do weird and wonderful things. Like I said here, life gets interesting because you can change the position of the masses. Okay, 3 examples, and we're going to run. First one, we have a spinning disc, like a pottery wheel, and we're going to throw onto that pottery wheel. So this is before, and then afterwards we're going to throw on a lump of clay. Okay, the moment of inertia is 1.6 kilogram meter squared without the clay, and it's successfully moving around at 5 rads per second. The clay has a moment of inertia of 0.25 kilogram meter squared, and after it's placed on, what is the new angular speed? think you know the answer, hit pause. Otherwise, here comes some solutions. Okay, I think we're going to take the equation from the previous one. The angular momentum before must equal the angular momentum afterwards. That means I, omega, must be I plus the new bit multiplied by a new speed. Let's plug in what we know. 1.6 times 5 gives us 1.6 plus 0.25 omega nu. Omega nu is going to be 1.6 times 5 over 1.6 plus 0. We know it's going to be smaller because this has been introduced, and that gives us a value of 4.3 rads per second. Good. Slightly more complicated version, much the same this time, another step involved. Let's imagine that we have a few more steps this time actually. Rotating disk is moving at 12 revs per minute, and then we deposit a mass of 50 grams at 0.1 of a meter around its axis of rotation. It now moves at 9 revs per minute. The question is here, what is the moment of inertia of the rotating disk? Right, if you think you know, hit pause, otherwise here comes the answer. Okay, a little trickier this one because you need to start doing some maths working out the new moment of inertia here. I knew. Why do we do that anyway? We say it's m mass times the radius squared, which gives us mass is 50 over 1,000 times 0.1 squared. Okay, but we do hold, the same equation does hold true. The moment of inertia times the angular speed gives us the moment of inertia plus the moment of inertia nu times the new angular speed. 12 revs per minute gives 12 revolutions per minute changed into seconds gives us the equation. However, because this is going to be constant on both sides, no, I'll leave it in, but it could drop out. Okay, let's do some rearranging. We want all the i's on one side. So we have I omega minus I omega nu. I've multiplied out this bracket, gives me I nu omega nu. Factorising gives us I nu omega nu over omega minus omega nu. Good, and that gives us in turn, the new one is going to be 50 over 1,000 times 0.1 squared. Omega nu is 9 times 2 pi over 60, because I'm converting to revs per minute into rads per second. And I divide that by omega, which was 12, minus 9, and let me factorise out the 2 pi over 60. That drops out with that, as I said before. And this gives us a value of, it's very tiny here, but the answer of, I have to use a calculator quickly. It gives us a value of 1.5, sorry this is so small, times 10 to the minus 3 kilogram meters squared. Okay, so much the same as we used before, but two more stages, working out the moment of inertia and rearranging. Okay then, let's talk about the last one. Let's have a rotating column, and let's say it has a moment of inertia of 4.4 times 10 to the minus 5 kilogram meter squared. it's running initially at 120 rads per second, but we're going to stop it and make it move backwards at the same speed, 120 rads per second, and that's going to happen in 50 milliseconds, a really fast change. Now what I want to know is three parts to this. I want to know first of all what's the angular acceleration that it undergoes. Then I want to know what torque is being exerted in order to achieve that. And then I want to know what the angular impulse is. In other words, as the change in momentum was the force multiplied by the time, or the change in momentum linearly, this was the impulse. So it's not hard to assume that converts into the change in angular momentum is the torque multiplied by the time, or the change in angular momentum is the angular impulse. Okay, if you think you know how to do these three, hit pause, otherwise here comes the answers. Okay, simply, the change in angular speed divided by time gives us the angular acceleration. We've moved from 120 rads per second minus, but we've got minus 120 because it's going the opposite direction, in 50 milliseconds. That gives us 240 over 50 times 10 to the minus 3. Careful of the milli, careful of the direction change. And that gives us 4.8 times 10 to the 3 rads seconds to the minus 2, careful of the unit. The torque is the moment of inertia multiplied by the speed, angular acceleration, alpha. We know that's 4.4 times 10 to the minus 5, multiplied by what we know here, 4.8 times 10 to the 3. And that gives us 0.21, careful about the units again. Torque is not only in force, but how far the force is acting away. The angular impulse, of course, is the torque multiplied by the time. 0.21 multiplied by the 50 milliseconds gives us a grand total of 1.06, so 1.1 times 10 to the minus 2, careful of the unit, Newton meter seconds. Okay, that finishes off the whole topic.